This will be a short video just looking at some of the introductory properties of the sun that we're going to be studying in a bit more detail here as we learn more about how the sun provides us with energy. A few sun facts. The sun accounts for 99.9% of the mass of the solar system. Most of the other 0.1% is provided by Jupiter, which weighs more than the rest of the planets and everything else put together. The sun's equatorial diameter is 109 times that of Earth. It's actually 1.8 times the size of the moon's orbit, and so quite a bit larger. The average density of the sun is just a little higher than that of Jupiter, so not terribly higher, but the amazing thing is how dense the sun is in its center. The density of water is 1 gram per cubic centimeter, so the density of the sun is 162 times that high. For most of us, the most dense material we encounter is lead, which is a bit more than 11 times as dense as water. Gold is more dense, about 19 times as dense as water. And if you've ever picked up, say, a man's gold ring, it's surprisingly heavy for the size of it. If you've ever picked up a platinum ring, that's about 21.5 times as dense as water. But a 2-cup portion of material from the sun's center would weigh 162 pounds on Earth, which is just amazing. Another amazing thing about the sun is that despite the fact that this material at the core of it is so dense, it is not a solid. It is acting as a particular form of a gas called a plasma. This is a state of matter that occurs when matter is heated to a high temperature or placed in a strong electric field. Electrons are liberated from atoms, leaving behind positive ions, and the positive ions and the negative electrons move about freely and independent of each other. You've actually seen this state of matter. It's the state of matter in a bolt of lightning or in a spark. It's actually a fourth state of matter after solids, liquids, and gases, and it's the most common type of ordinary matter in the universe because ordinary matter in the universe is mostly in stars. Here are some of the prominent elements in the makeup of the sun. Different sources may give you slightly different numbers than these. The first two numbers I took from Wikipedia, which I thought might be more up to date than your textbook. You can see that by mass, the sun's about 3/4 hydrogen and 1/4 helium. All the other elements combined from oxygen on down account for less than 2% of the mass of the sun. The sun looks very turbulent when you view it in wavelengths of ultraviolet light. This 19.5 nanometer spectral line, or 195 angstroms, is material that's at about 1 million Kelvin. And this is a picture taken from back in 2000 near solar maximum. That was the maximum of sunspots. The wavelength that you're looking at here, 17.1 nanometers, is produced by iron atoms which have had 8 of their electrons stripped off in violent high temperature collisions. The observatory is in a geosynchronous orbit that allows the spacecraft to communicate with a single ground station, so it stays within view of that ground station as the Earth rotates. In that orbit, it can have a nearly continuous view of the sun. There are just a few weeks of the year when the sun would be blocked by the Earth for about an hour a day. The rest of the time it's always in view. The sun actually takes about 25 days to turn on its axis, so this time-lapse video is way sped up. But look how crazy violent the surface of the sun is. You see a lot of loops of material coming off of the sun and then coming back to it. It's impossible in the picture to know where it comes off and where it lands. The material in those loops is actually traveling along the magnetic field lines of the sun. The sun has a very complex and strong magnetic field. If you want to watch this video yourself, you can go to YouTube and then do a search for that SDO:year 6 Ultra HD. It's actually about 6 minutes long or so. Here's a picture of a solar prominence. That's what we call this. It's a bunch of material launched off of the sun that will eventually fall back down onto it. This picture was taken with a filter that allows in light of wavelength 656 nanometers, and it's produced by hydrogen atom. That's the bright red spectral line that you see if you look at a hydrogen spectral tube. This picture gives a sense of scale to the solar prominence. Our planet looks pretty puny compared to the processes that are going on the sun. Some more sun fact. We're interested in learning about the way the sun produces power. Power is the rate at which the sun converts energy of some type into light. The units of power, the watt, is 1 joule per second, where a joule is the metric system unit of energy. And if you pick up a pen and hold your hand up about as high as you can reach and drop that pin onto your toe, a pen like a writing instrument, it'll have about a joule of energy when it hits your foot. That's about how much a joule happens to be. So the sun produces 3.86 times 10 to the 26 joules per second of energy. We can do a simple experiment in the classroom with a 100-watt light bulb and a ruler and a student's hand and come up with a measure of the intensity of light from the sun. First thing we would do is on a nice sunny spring day, go outside and hold your hand out, feel how bright or how warm the sunlight feels on it. Then we go back into the classroom and have you put your hand near a 100-watt light bulb until you feel the same warmth. And from that, we can come up with a measure of the amount of energy from the sun. I've been doing this in the classroom for more than 25 years, and every time we do it, we get something close to the value that you see here, which is measured with very sophisticated instruments. We always get the times 10 to the 26th part correct, but usually we're a little lower than that. We usually get 2 or 3 times 10 to the 26th. We're not using a very sophisticated instrument, just your hand and how it feels out in the sunlight. The sun has been providing this much power for billions of years, somewhere in the neighborhood of 4.6 billion years. In the early 20th century, the early 1900s, scientists realized that the methods of energy production with which they were familiar just could not provide that much power for that long. Chemical reactions like burning coal or gasoline couldn't do it, nor could gravitational contraction, which you can read about in your textbook. Eventually, as they learned more about atoms and then nuclei, they realized that it had to be a process involving the nuclei of atoms. And a nuclear reaction for a single nucleus will produce roughly 1 million times the energy of a single atom chemical reaction. Nuclear reactions are the type that can work over the large time span required. We'll learn about these. It is nuclear fusion that powers the sun. We'll look at that in a later video.